Hello, in this lecture we will cover basic circuit elements. Specifically, we will cover today independent and dependent sources, transducers and sensors, and also switches. Sources supply energy to a system. In electrical circuits, we have voltage and current sources. An independent source is a voltage or current generator, not dependent on other circuit variables. An ideal voltage source has the voltage fixed and the current is determined by the circuit. Similarly, an ideal current source has the current fixed and voltage is determined by the other elements of the circuit. Actually, an independent voltage source is not always fixed. For instance, if we have a battery with 9 volt nominal voltage, if we start to withdraw a high amount of current from the circuit, then the battery voltage will start to decrease. However, for simple cases, we consider this battery at constant 9 volts such that we can have a simple model. For us, good enough is good enough, and we try to make things simple but not simpler as long as it works for the specific problem we are solving. These simplifying assumptions are always made in engineering. In order to analyze electrical circuits in real world, we do lots of measurements. Specifically, we measure voltages and currents. In order to measure currents, we are using the ammeter. We are putting the ammeter in series with the circuit element such that the same amount of current passes through this ammeter as well, and the ammeter measures this current. Similarly, we just measure the voltage of an element by putting the probes of the voltmeter at the two terminals of this element, and that way we are measuring the voltage between these two terminals. Here we have a voltmeter between these two terminals. We are assuming that the voltmeter behaves like an open circuit such that it does not change the behavior of the circuit. Otherwise, current would flow through the voltmeter. But this is not possible because voltmeter behaves as an open circuit. Similarly, here we have an ammeter, and ammeter behaves like a short circuit. In other words, it just does not alter the flow of the current. Therefore, it does not change anything in the regular operation of the circuit. Again, these are simplifications. Voltmeters have their internal resistance, and ammeters are not behaving like perfect short circuits. However, for most of the applications, these simplifications are valid. In practice, we don't have separate voltmeters and ammeters. We use multimeters that are capable of measuring voltage, current, and resistance. Indeed, most of the multimeters right now measure other things such as capacitance, inductance, temperature, forward diode drop, and frequency of electrical variables. In electrical circuits, especially in electronics, we have devices such as transistors and amplifiers, which can be modeled using dependent sources. In dependent sources, the voltage or current of one circuit element is proportional to the voltage or current of another circuit element. For instance, here we just observe that we have a dependent source, and here the value of this dependent source is 5 times I. We look to the part of the circuit where I is defined. I is the current passing through these 18 ohm resistor. So in other words, the voltage value of this part, this source, will be 5 times I, whatever that I value at that instant will be. Similarly, here we have a voltage dependent current source. The current value of this dependent source will be equal to 0.2 times the voltage over this resistor. In a sense, we have 4 different types of dependent sources. We have a current controlled voltage source. So in other words, here the voltage VD is equal to R times IC. IC is the control current and VD is the dependent voltage. Similarly, we have voltage controlled voltage source VC, Vs. Here, the voltage VC, the control voltage, controls the voltage value of this dependent source. VD is equal to B times Vc. Similarly, we have voltage and current controlled current sources. Here in this example, we have a voltage controlled current source. The voltage value Vc controls the current being supplied by this element. And in the last example, we have a current controlled current source. The current IC controls the current ID. ID is equal to a constant value times IC. Here on the screen, we see a bipolar junction transistor, which is a three-terminal device. The current through the base controls the flow of a larger current between the collector and emitter. And we can model this transistor using a dependent source and the circuit shown here. Here, specifically, the voltage between the emitter and the base controls the current flowing from the collector to the emitter, because here we have a voltage dependent current source. The current through the transistor IC is proportional to the voltage BE. Specifically, IC is equal to Gm times VBE. Let's look at the circuit on the lower left side. It would be very hard to analyze this circuit because we just don't know what this element does. Therefore, we replace this transistor at the specific operating condition with this new circuit, which consists of elements which we can analyze, resistors and dependent sources, and that way we can utilize our circuit analysis tools and methods in the analysis of this circuit. Let's understand the concept of dependent sources by solving an exercise. Here we need to determine the power absorbed by the voltage controlled voltage source. So first we find the voltage controlled voltage source, and it is this element. And current ID is passing through this element. Since it is passing through the positive terminal, it adheres to the passivity convention, and therefore the power absorbed is equal to ID times VD. We need to find the values of ID and VD. ID is very simple because the current ID is passing through this element, then here, then it passes through the AM meter and then goes this way. And AM meter shows the value of 1.5 amperes. VD is a little bit more complicated. VD is equal to 2 times VC. Therefore, we need to find the value of VC. Value of VC is being measured by the voltmeter, and it is equal to 2 volts. Therefore, VD is 2 times 2 volts, which is equal to 4 volts. In order to find the power absorbed, we need to multiply ID with VD, which is equal to 1.5 amperes times 4 volts, which is equal to 6 watts. A transducer converts energy from one domain, such as electrical, mechanical, hydraulic, thermal, pneumatic, magnetic, chemical, or something else, to another. Transducers are usually used to convert electrical signals to and from other physical quantities, such as energy, force, torque, light, motion, and position. The process of converting one form of energy to another form is known as transduction. And if we are converting a physical quantity to an electrical signal, then we are doing sensing, and those devices are called sensors. Here is an example for a transducer, potentiometer. Potentiometers convert position to resistance. Potentiometer is, in a sense, a resistor having a third contact called as wiper, which slides along the resistor. So it's a three-terminal device, 1, 2, and 3. Two parameters of the potentiometer are A and Rp, such that we can describe the potentiometer. Specifically, A is the parameter which divides the potentiometer to two resistors, the sum of which is equal to Rp. For a rotary potentiometer, the position of the wiper corresponds to the angular position of the shaft connected to the potentiometer, and this way we use these potentiometers as sensors for robots and other mechanical devices. Another example of a transducer is a temperature sensor. For instance, a temperature sensor AD590 from the company Analog Devices can be modeled as a current source having proportional current to the temperature. This device works in the operating condition when the voltage is between 4 and 30 volts. When the voltage is in this operating range, the output current is proportional to the temperature. So we have here the sensitivity of the sensor K is equal to 1 microamperes per Kelvin. So in other words, for a 1 Kelvin temperature change, the output of the sensor changes by 1 microamperes. In the previous slide, we considered the AD590 temperature sensor from the Analog Devices company, and we stated that it has an operating range. How do we know the operating range of this sensor? In order to know this, we look to the datasheet of this sensor. In the datasheet of this sensor, we have information on the operating temperature, power supply range, the sensitivity, the package information, and more. A good engineer should be able to read datasheets of different devices such that he or she can implement new systems utilizing these components. All electrical systems have switches. For instance, in order to open a device, we just click to the turn on switch. Switches have two distinct states, open and closed. An ideal switch acts as a short circuit when it is closed, and it acts as an open circuit when it is open. Here are some different types of switches. On the left, we have single pole, single throw switches. Here, the switch is initially open at t is equal to 0. It closes, connecting this part of the circuit with this other part. And here, we have an initially closed switch, which at t is equal to 0 breaks the connection between the left part and right part. Similarly, on the right side, we have single pole double throw switches. Here, at t is equal to 0, the connection between C and A is opened, and the connection between C and B is closed. Here, we have the same single pole double throw switch, but here it is make before break. In other words, at an infinitesimal small time instant, at t is equal to 0, both A, B, and C are connected to each other. Afterwards, the connection between A and C is getting opened, and the A, B, and C continue to be connected. So, how will we analyze circuits with multiple switches? Here we have a switch which closes at t is equal to 0. Here is another one which connects to the right side of the circuit at t is equal to 2. And here is another one which opens at t is equal to 0. So here we have three important time instances. What happens when t is less than 0? What happens between t is equal to 0 and 2 seconds? And the third one, what happens when t is greater than 2 seconds? When t is less than 0 seconds, we just have this part open. Here we just have this connection to the left, and Before t is equal to 0, this side is a short circuit. So this is the condition of the circuit before t is equal to 0. Between t is between 0 and 2 seconds, we just have this element getting closed, this element getting opened, and we still are connected to the left side for this upper switch. And after t is equal to 2 seconds, this element maintains its contact. This is still open, and this single pole, double pole switch, double throw switch is connected to the right side. As you can see, we have modeled this circuit with 3 switches using 3 circuits which are valid for different time periods, which have only open and short circuit connections. In this exercise, we need to draw the current I versus time. In order to solve this, we need to find the important time instants. One of them is t is equal to 3 seconds when this switch opens. Another one is t is equal to 5 seconds when this switch closes. Let us draw the equivalent circuit for t is less than 3 seconds. When t is less than 3 seconds, the left side will be an open circuit, right side will be a closed circuit. Equivalent circuit will become something like this. And accordingly, I will be equal to 6 volts divided by 3 kilo ohms, which is 2 milliamperes. Secondly, let us consider the time t between 3 seconds and 5 seconds. Between 3 and 5 seconds, both switches are open, so indeed the circuit is in this configuration. Here I have 12 volts, but it is not connected to the resistor. I have 3 kilo ohms and current I flowing through that, whatever that current might be. And I have this part is also open, connected to the 6 volt source. So no current can flow on the left side. No current can flow from the 6 volt source. So in other words, I will be equal to 0. Let's look at the third condition. Third condition is when we have t is greater than 5 seconds. When t is greater than 5 seconds, the left side of the circuit is closed. We have here 3 kilo ohms, current I passing through that, and here I have my 12 volt source. So I will be equal to 12 volt divided by 3 kilo ohms, which is equal to 4 milliamps. So we have less than 3 seconds, 2 milliamps. Between 3 and 5 seconds, 0 amps. And above 5 seconds, 4 milliamps. Now we need to draw this. My x-axis is time in seconds. My y-axis is I in milliamperes. And I write the important times 3 and 5. Here, until 3, we just have 2 milliamperes. Between 3 and 5, I have 0. And after 5, I have 4 milliamperes. And this is my graph, 2, 0, and 5.